So next, let us discuss the stress versus strain curve, very important topic. Okay. So let's suppose we have a metal wire. Okay, we have some metal wire which is hung from some rigid support from some roof, and we connect a pan to this metal wire. Okay, we connect a pan over here, and we keep on adding weights in this pan. Okay, so we keep on adding some weights, right? So now, while we add these weights, some internal restoring stress is generated. Okay, so that stress will be equal to this externally applied stress only, and there will be some elongation in this wire. Okay, so we measure that elongation using micrometer screw gauge, and we plot a curve between stress and strain. Okay, so that is stress strain curve, right? So the stress versus strain curve looks something like this. Okay, not something like, it looks like this for most of the metals. Okay, and we want to understand this curve. The stress is plotted on y-axis and strain is plotted on x-axis, right? So now we add some weight, we record the extension, we find out the stress and strain. Okay, and we plot the points. So you can see on this graph, from this point 0, or you can say O, to this point A, the graph looks straight, right? The graph looks straight. Okay, so the graph obeys Hooke's law. What is Hooke's law? Under the elastic limit, stress is directly proportional to the strain. So stress is directly proportional to strain, and the proportionality constant between them is Young's modulus. So stress is equal to y multiplied by strain. Okay, this is what we know. So y is equal to what? Stress upon strain, right? So if you find slope of this graph, okay, slope of this graph till the time it is a straight line, then you will get the value of Young's modulus of this material. Okay, so you will get value of the Young's modulus if you take slope of this graph. Okay, till this time. Now if you keep on adding the weights, what happens? The length of wire increases. If you remove the weights, what will happen? The length is restored back. Okay, if you remove the weights, what will happen? The length is restored back. That means the wire is elastic. Okay, the wire is completely elastic. Now it is completely elastic till this point A. Till the point A, the stress is directly proportional to strain. So this point is known as the proportionality limit. Okay, point A is known as proportionality limit. You can see here. After that, so after point A, what happens? Now, for little increment in stress, there is more increment in strain. Okay, so till the point A, you needed more stress for little increment in strain. So comparatively, now you need lesser stress. Okay, lesser stress for same amount of increment in strain. Okay, so the wire elongates easily after this point A, but it is still elastic. It is still elastic. So if you remove the weights, it will still regain its original length. Okay, so point up to which it is completely elastic, it is known as the elastic limit, or it is also known as the yield point. So what is yield point? It is denoted by this point B on the graph. What is point A? It is proportionality limit. What is point B? It is the yield point. So till the point B, wire is still completely elastic. That means if you remove the weights, what will happen? the wire will completely regain its original length. Is it clear? Okay. So point A is proportionality limit. Point B is the elastic limit, or it is also known as the yield point. So what happens after point B? So now for very little increment in stress. So here you can say, you can see this graph is almost flat. Okay, so for very little increment in the stress, there is large increment in strain. That means there is very large elongation. Okay, so here, and that's why we say that wire is yielding. Okay, therefore this point is known as the yield point. Okay, so after the yield point, what happens? Wire is yielding. Okay, wire is yielding means it flows. Okay, so after this point, for very little increment in stress, there is large increment in the length of wire. There is large increment in the strain. Okay, and it continues till this point C. Okay, so now the wire is no longer elastic. So wire will not regain its original length if you remove all the weights. Okay, so what happens now? If you remove all the weights from this point, okay, if you remove the stress, external stress, then still some permanent elongation is left in the wire. Okay, this much permanent elongation is left in the wire, and it is known as set. Okay, it is known as what? Set. Okay, or permanent set, you can say. So is it clear? Then see, so we have seen from point B to C what happens for very little increment in stress, there is large increment in strain. Okay, after point C, once again, now the wire has yielded, but after this point C, what happens? Again you have to increase the stress. Okay, so now wire doesn't flow that easily. Now again you have to increase the stress. Okay, so you can see the slope is increasing, right? So that means more stress is required for same amount of strain. Okay, so if you consider, let's suppose this much strain from B to C. Okay, so from B to C very little stress is required, but after this point C, okay, comparatively larger stress is required for same amount of strain. Okay, and this continues till the point B, but now compared to this region OA, which is the elastic region, now very little stress is required. Okay, compared to this region, little bit more stress is required, but compared to this region, compared to OA, very little stress is required for same amount of strain. Okay, so this region from B to D, okay, the wire is, I'm sorry, the wire is flowing. Okay, wire is flowing. So this is known as plastic region. This is known as what? Plastic region. And this flow is known as plastic flow. Okay, why it is known as plastic flow? Sorry, why is it known as plastic flow? It's because wire is not going to regain its original length. Okay, that permanent deformation will remain there, right? That's why it is known as plastic flow, and this behavior of the wire, it is known as plastic behavior. Okay, the wire is no longer elastic. All right, so you can keep on increasing the stress till this point D. Okay, you can keep on increasing the stress on the wire till the point D, and the stress corresponding to this point, it is the maximum stress which can be beared by the wire. Okay, so this is the stress corresponding to this point is known as the ultimate tensile strength of the wire. It is known as what? The ultimate tensile strength of the wire. The wire cannot bear any more stress. So now once this point is reached, what happens? A neck is formed in the wire. Okay, So a very thin region is formed in the wire. It is known as neck. And after that, now even if you reduce the stress, the strain will increase. Okay. So after the point D, even if you reduce the stress, what will happen? The strain will increase. Okay. And one point will come where the wire will break. So that point is known as the fracture point on the graph. Okay. So that point is known as the fracture point. Right. So point D is the point corresponding to maximum tensile strength. Right. So this is how the stress versus strain curve for the metals will look like. Okay. Now after this, so we can gain some information from stress versus strain curve of a material. So what kind of information do we get? So think about these 2 points. So point D is point corresponding to maximum tensile strength, which can be beared by a wire or a material, and point E is the fracture point or breaking point. Okay. So if these 2 points are very close, what can we say about the material? The material is brittle. Okay. If point D and point E are very close, then we can say that the material is brittle. Okay. If point D and E are very close, then we can say that material is brittle. It breaks very easily. Okay. Right. And then if D and if D and E are far apart, okay, if D and E are separated by a very large distance, you can say, okay, by large distance, then we can say the material is ductile. Okay, then the material is ductile. Okay, that means there can, okay, sorry, there can be more strain in this kind of material even after the point corresponding to maximum tensile strength is reached. There is a large elongation in this wire before breaking. Okay, that means these kind of materials, they can be stretched and they can be formed into wires. Okay, so these materials are ductile materials. If the distance between D and E is very large, the material is ductile. It will not break easily. Okay, before breaking there will be very large elongation in these kind of materials. But if D and E are very close, then the material is brittle. Once the tensile strength, sorry, the point corresponding to maximum tensile strength is reached, it breaks very fast. Okay, so those materials are brittle. Is this thing clear? Let's talk about the elastic potential energy. Elastic potential energy of a wire. So let's suppose we have some wire and we apply some weight to that wire. Okay, we apply some force to the wire. So we have this wire and we apply some weight to this wire. So suppose this much was the original length of the wire. Okay, so from here to here, this much is the original length of the wire, capital L, and this much is the extension in the wire. Okay, so this much is, let's call it delta L. It is the extension in the wire. Okay, so now how much is the force? Force is equal to this weight. Okay, force acting on the wire is equal to what? This weight. Suppose wire itself is weightless. Okay, So now, how much would be the work done? Okay, how much would be the work done in this process of extension? Okay, so we can say for small extension, let's call it DL. The work done, the work done will be equal to what? dW, and it is given by F dot dl, right? It is given by F dot dl. Suppose that small l, okay, small l is some intermediate extension, is intermediate extension in the wire. Okay, what is small l? It is, now you are extending the length of the wire from 0 to delta l. Okay, and in between there is some point where when the extension is smaller, then what we can say that the Young's modulus is equal to F upon A, okay, and dividing by the strain is equal to multiplied by its reciprocal. So L, okay, I want to divide by small l upon capital L, so I will multiply by capital L upon small l. Okay, so now the force therefore can be written as what? Ya times L divided by capital L, right? The force can be written as YAL upon capital L, and this thing I will substitute here. Okay, so therefore the work done can be written as what? Force is Ya small l upon capital L, Ya small l divided by capital L, and the small displacement is dl. Okay, so now when you stretch that wire by length small l, there is already some restoring force, and against that restoring force again you stretch the wire by dl. Okay, dl is very short increment in the length of wire. Okay, so now what you do is, okay, initially the increment was 0 and the maximum increment is delta l, right? So the increment uh, in the length of the wire changes from what? 0 to delta l. Okay, so work done in this process. So work done when the length of the wire increases, the length of wire increases at delta L. Okay, so work done is W. It is integral of this thing. It is integral of dW, that is YAL upon capital L dot dl. Okay, and the extension changes from 0 to delta L, right? So y is constant, a is almost constant, we can say, for small increment. Okay, actually what will happen when you increase the length of wire, when you stretch a wire, the area will decrease, but for small increment in the length, we can say area will fairly remain constant. Okay, so we'll take it outside. So y, a and l I will take outside. So then I'm left with integral from 0 to delta L of L dl. And what will be this integral? So this integral is equal to what? It is delta L square divided by 2. Okay, actually it is L square upon 2, right? Then you can apply the lower and upper limit. So since lower limit is just 0, it is delta L square divided by 2. So work done is equal to Ya upon L multiplied by delta L square divided by 2. Okay, so is it clear? After that, see, you can write force as Ya upon L multiplied by the extension, right? So what I can do is I can rewrite this work done. Okay, I can write this as half of Ya multiplied by delta L upon L multiplied by delta L. Okay, so what is this thing? So this is the final force. Okay, so when you are increasing the length by delta L, so when increment is delta L, force acting on the wire, the restoring force acting on the wire is equal to what? Ya multiplied by delta L upon L, right? So the work done can be written as half of this force multiplied by delta L. Okay, and the force is called as load. So it is half of load multiplied by extension in the wire. Okay, so work done is written as half of load multiplied by extension. Okay, and this work done gets stored as the potential energy of the wire. Okay, so when you remove the external forces, what happens? The wire regains its original shape and size. Okay, so for that it will have to do some work, and that work is done using this energy. Okay, so this work done gets stored as the elastic potential energy of the wire. This work gets stored as the elastic potential energy of the wire. So elastic potential energy can be written as U equals to half of load multiplied by extension. Okay, and then what I can do is I can divide this potential energy by volume. Okay, so I can find out the elastic potential energy per unit volume. Elastic potential energy per unit volume. So I will denote it by a small u. It is capital U divided by V, and it is equal to what? Half of load. Load is F multiplied by extension is delta L, and I will write volume as A multiplied by L. Okay, I will write volume as A multiplied by L. So what I have done is I have just written this formula of U, and I have divided by V. V is area of cross section multiplied by length of the wire. What do I get? I get elastic potential energy per unit volume is equal to half of F upon A, this is stress, and delta L upon L is strain. Okay, so small u is equal to half of stress multiplied by strain. Okay, so potential energy per unit volume is equal to half of stress into strain. This formula we get. After that, this formula can be written in various ways like this. So you can use y is equal to stress upon strain, y is equal to stress upon strain. So stress can be written as y multiplied by strain. Okay, and therefore you can write u is equal to half of y multiplied by strain square. Okay, because stress is y multiplied by strain. And then you can substitute strain is equal to, if you take strain on left hand side, you get stress divided by y. You can put it here. So you get this another formula, u equals to half of strain square, sorry, stress square upon y. Okay. So you get these three formulae for elastic potential energy per unit volume. Is it clear? After that, let's talk about thermal strain and thermal stress. So what is thermal strain? So sometimes, not the, I'm sorry. So what is thermal strain? So uh, we know that in order to increase length of the wire, we need to apply some external load, right? In order to increase length of the wire, we need to apply some external load. Okay, but if there is increment in temperature, if there is sudden rise, sorry, if there is sudden rise in the temperature, still the length of the wire can increase. Okay, so we have seen that if you apply some load to the wire, its length will increase, but the length can increase due to sudden rise in temperature also, due to rise in temperature also. Okay, so now the strain caused in wire because of rise in temperature is known as thermal strain. Okay, very simple. So let's suppose the delta T is rise in temperature, delta T is rise in temperature, and it causes this much change in length. Delta L is change in length of wire. Okay, so we can say that this delta L is directly proportional to delta T. Okay, more is rise in temperature, more will be the change in length, more will be increment in length, right? Okay, experimentally we find this, that this delta T is directly proportional, sorry, experimentally we find it that delta L is directly proportional to delta T. Okay, not delta T square or not delta T raised to half or something. Okay, so you might say even if it is delta T raised to half, right? Even if delta L is proportional to delta T raised to half, still there will be increment in length if there is rise in temperature. If it is delta T, it is proportional to delta L is proportional to delta T raised to 2. Still there is increment in length if there is increment in temperature. Okay, so how do we know that delta L is proportional to delta T only? So we know this from experiments. Okay, nothing else. Okay, so delta L is directly proportional to delta T. What else will it depend on? So of course the change in length will be more if the length of wire is more, right? For an example, we have wire, or let's suppose we have these two rods of same length. Okay, now temperature increases, so what will happen? The length of this rod will increase. Let's suppose this much, length of this rod increases this much. Okay, their original lengths were L and L, and increment is delta L and delta L. So now what you do is you connect those two rods together. you stick those two rods like this. So now you get this big rod having twice as much length compared to this rod. Okay, so now how much will be the increment in the length? It will be 2 times of delta L, right? For same increment in temperature, the increment in length will be 2 times of delta L. Okay, and that's why what we can say is delta L is directly proportional to length of the wire. So if we combine these two, what do we get? We get delta L is proportional to what? L times delta T. Okay, so change in length is proportional to L times delta T. And if we remove this proportionality sign and put an equality sign, a constant will come, and the constant is denoted by alpha. It is denoted by alpha, and it is known as coefficient of thermal expansion. It is known as what? Coefficient of thermal expansion. So delta L, the change in length, which is final length minus the initial length of the wire. Okay, it is equal to what? Alpha multiplied by L delta T, and alpha is known as coefficient of thermal expansion. Okay, and you can take this L on the other side, and so you can take L on other side, and you can write that thermal strain caused in the wire is delta L upon L, and it's equal to alpha times delta T, right? Thermal strain is equal to what? Alpha delta T. Okay, if you take L on other side, you get this. And then I know that Young's modulus of the wire is stress upon strain. Okay, so I can find out thermal stress in the wire. So stress produced in the wire because of rise in temperature. Thermal stress, okay, can be written as what? Y multiplied by thermal strain, right? So it is equal to Y multiplied by alpha delta T. This is the thermal stress produced in the wire. Okay, so stress produced in the wire because of rise in temperature. Is it clear? So this is the end of this chapter, right? This is very short chapter, but you can expect one question based upon this chapter. Okay, so let us solve some more questions. Right, let us discuss these questions. Copper of fixed volume V is drawn into wire of length L. When this wire is subjected to a constant force F, the extension produced in the wire is delta L. Which of the following graphs is a straight line? So we want to find out which of these graphs is a straight line. Okay. Okay. For a question based upon elasticity, always start from Young's modulus. Okay, you have some extension, some length, etc., etc. We can start with Young's modulus. So Young's modulus is F upon A multiplied by L upon delta L, right? So now if I move this delta L on left hand side, what can I say? Delta L is equal to F upon A multiplied by L upon Y, right? But see, delta L here will be proportional to L if all of the other quantities are constant. Okay, if all of the other quantities are constant, we can say that delta L is proportional to L. So see what is constant. So copper of fixed volume. So volume is constant, not the area, right? So area is not constant. Okay, it is drawn into wire of length L when it is subjected to constant force F. F is constant, Y is constant, but A is not constant. But what is constant? Volume is constant. So let us adjust volume there. Okay, so let's adjust volume. So we have F upon A multiplied by L. Okay, so I'm multiplying denominator by L. So I have to multiply numerator also by L, right? So then what do I get? I get F upon Vy, V is volume. Okay, now all of these things are constant. Okay, so what do you get? Delta L is equal to this constant multiplied by L square, right? So it is equal to this constant multiplied by L square. Okay, so if you take ratio of delta L to L square, it is a constant, or delta L is equal to constant multiplied by L square. That means if you plot graph between delta L and L square, it will be a straight line. Okay, so this is the question. Which graph is a straight line? So this graph is a straight line. Graph between delta L and L square. Next question. The following four wires are made of same material. Which of these will have largest extension when the same tension is applied? This is the question. Okay. So length and diameter of four wires are given. Which of them will have largest extension? This is the question. When same tension is applied. Okay, let's try to solve this. So we know that y is equal to F upon A multiplied by L upon delta L. So delta L can be written as F upon Y. These two are constant. Okay, same tension is there, multiplied by L upon A, and A can be written as what? Pi r square, right? We have diameters in the options, so we'll adjust diameter there. Okay, so we want diameter square, so we'll multiply this r square by 4. Okay, and we'll divide by 4. So this is equal to 4 upon 4f upon pi y. Okay, this is a constant, multiplied by L upon diameter square, right? So delta L is directly proportional to length, inversely proportional to d square. Okay, so let's put the values. First one, so it is 200 divided by 2 square, that is 4, right? So this is some constant, let's call it k, and we just have to find out this factor now. Okay, L upon d square. Okay, so 200, we don't care about units because units of all the parameters are equal in all options. Okay, so it is 200 by 4. First one is A is 200 by 4, 50. B is, okay, 50 means 50k. B is 300 divided by 9. Okay, so it is how much? It is 100 divided by 3, 33.3. C is 50 divided by zero point 0.5, right? So it is 500 upon 5. It's 100. And option D. Okay, option D is 100 divided by 1. Oh, so we are having tie here, right? Option D and no, it's 0.5 square in option C. So it is 0.25, right? So this will be 200. Okay, so option C would be the answer, right? So if my calculation is correct, I think it is correct. There is, okay, 0.5 square is 0.25, right? 5 multiplied by 10 raised to 1. Okay, 10 raised to minus 1. 25 multiplied by 10 raised to minus 2, right? Okay, this is clear. Simple question, right? But lengthy. Next one. If the ratio of diameters, lengths, and Young's modulus of steel and copper wires shown in figure are P, Q, and S respectively, then the corresponding ratio of increase in their lengths would be. Okay, so the ratio of lengths is P, length of steel upon length of copper is P, then Young's modulus of steel divided by Young's modulus of copper is Q. This is given. No, ratio of diameters is P. Okay, so ratio of lengths is Q. Ratio of Young's modulus is S, and ratio of diameters of the steel and the copper, okay, is equal to P. This is given. Okay, and we want to find out corresponding increase in their lengths would be. So most of the times the increment is length, increment in length. There are questions based upon increment in length only. Okay, so it's good to memorize this formula. Delta L will be equal to what? F upon AY multiplied by L, right? And A can be written as what? Pi r square, or we can write it as, we want diameters. Okay, so we can write 4d square. Okay, and y will be there. So after that we just have to take the ratio. So delta L of steel and delta L of copper is 4 upon pi. This will be constant, right? Into force acting on steel. Okay, so force acting on steel, it's here. It is, this mass is 2m, this mass is 5m. So total force on steel wire, it will be what? 2m plus 5m multiplied by g. That is 7m multiplied by g. Okay, so for now let's keep it as this. Force on steel, length of steel upon diameter of steel square multiplied by y for steel. I'm sorry. And I want to divide it by, okay, same thing. So 4 by pi, force of force on copper, length of copper divided by diameter of copper square multiplied by Young's modulus of copper. So it goes into the numerator. So diameter of copper square multiplied by Young's modulus of copper. So this thing gets cancelled. 4 by pi and 4 by pi. Okay, this thing gets cancelled. After that, what do we get? We have force on steel. So it is 7 mg upon force on copper is 5 mg. So is there 7 by 5? There are two options. Okay. Multiplied by length of steel upon length of copper. Okay. Multiplied by diameter of copper upon diameter of steel. And we have square of that. Multiplied by, you have Young's modulus of steel in the denominator and Young's modulus of copper in the numerator. Okay. So this is equal to 7 by 5. Length of steel upon length of copper is Q. So 7 by 5 multiplied by Q. Length of, diameter of steel upon diameter of copper is P. So we have reciprocal of that. So it's 1 by P square multiplied by 1 by P square and multiplied by, you have Young's modulus of copper upon Young's modulus of steel, and again you have reciprocal of that. Okay, so it's 1 by S. So 7 by 5 Q upon P square S is the answer, and it is option B. Two wire of same material having radius in ratio 2:1 and lengths in So two wire of same material having radius in ratio 2:1 and lengths in ratio 1:2. If same force is applied on them, then the ratio of their change in length will be. So again, this is simple question, right? We just have to do like last question. So change in length is given by what? It is F upon AY multiplied by length. Okay. So for first wire, let's call it delta L1, L1 and A1. So A1 can be written as, okay, let's keep it as it is, and let's divide it by delta L2, which is equal to F. They are pulled by same force, right? So F is same upon A2 Y multiplied by L2. Okay, we are dividing these two. So FF gets cancelled, YY gets cancelled. It is the same material, and we get delta L1 upon delta L2 equal to A2 upon A1 multiplied by L1 upon L2, right? So what is A2 upon A1? It is R2 upon R1 square, because area is directly proportional to radius square. R2 upon R1 square multiplied by L1 upon L2. So what is L1 upon L2? Radius in the ratio is 2:1 and length in ratio 1:2. That means R2 upon R1 is also 1:2. Okay. So it is 1:2 square multiplied by 1:2. 1 upon 2. Okay. So that is 1 by 8. 1 by 2 square is 1 by 4. 1 by 4 multiplied by 1 by 2. 1 by 8 is the answer. Option D. The Young's modulus of the material of wire of length L and radius R is Y. If the length is reduced to L by 2 and radius R by 2, the Young's modulus will be. Tell me the answer. Young's modulus of a wire is Y. If length is reduced to L by 2, radius to R by 2, what will be the resultant value of Young's modulus? This is the question. It's property of material, okay, not a wire of particular length and radius. So it will remain as it is. Young's modulus is property of material. For a fixed material, it will be fixed. Okay. It does not depend on length or area of cross section, etc., etc. Next question. When a block of mass m is suspended by a long wire of length L, the length of wire becomes L plus L. The elastic potential energy stored in the extended wire is. Tell me. This is very simple, right? Direct formula. What is elastic potential energy? Half of load into extension, right? So it is half of mg multiplied by extension is L. Okay, mg multiplied by L. This is the answer. Okay, it is half of load multiplied by extension. That is mg multiplied by L. Direct formula. Okay, very simple. See, if we see NEET questions, no, recent NEET questions, 2019, there was 2020 question. Okay, so in this one at least you have to do some calculation. In this one also some calculation. Okay, this one also was little bit different. But from 17, this was 18, okay, 20. The questions have been very easy, right? So this chapter, definitely there will be one question. Okay, I mean, how much definitely? 99%, right? Because there have been one or two questions in the past. Okay, and question will be easy. Okay, next question. Wires A and B are made up, sorry, not made up. Wires A and B are made from same material. A has twice the diameter and 3 times the length of B. If the elastic limits are not reached when each is stretched by the same tension, the ratio of energy stored in A to that of B is. Tell me. A has twice diameter and 3 times length of B. So extension delta L in A is equal to what? It is F upon A, F upon AY multiplied by LA. So it's the same material and force is equal. Okay, they are stretched by same tension. So just area of cross section is different. So this is for A. Similarly, you can write an equation for B. So LB is equal to F upon AB into Y multiplied by, sorry, this is delta LB. Okay, extension. Right. Sanjay is saying option B. Let's check. So F and Y gets cancelled. It is LA upon LB multiplied by AB upon AA. So how much is LA upon LB? A has twice the diameter and 3 times length of B. So diameter is, sorry, length is 3 times and diameter is twice. Okay. So diameter of A is twice. That means AB is to AA is half square. Okay. Diameter square. So it is, yeah, 3 is to 4. Right. 3 by 4. This is the answer. Option B. Young's modulus of the material of a wire is Y. On pulling the wire by a force F, the increase in length is X. The potential energy of the stretched wire is, again, same question, different exam, same question. Tell me. Option, so option A, right? Potential energy is half of load into extension. Half of the external force multiplied by extension. Two wires of same material and same diameter have lengths in the ratio 2:5. They are stretched by same force. Okay, same material, same diameter, lengths are in the ratio 2:5. Then the ratio of work done in stretching them is. So again, this is also simple. So delta L is directly proportional to L, right? Okay, and lengths are in the ratio 2:5. Okay, so work done is equal to half of force into extension. Okay, extension is directly proportional to length. So W1 equals to half of F into delta L1. W2 equals to half of F multiplied by delta L2. If you take ratios, then half F gets cancelled. Delta L1 upon delta L2 will be what? 2:5, because length ratio is 2:5. Okay, so it is option B. I'm sorry, there was one more topic called Poisson's ratio. So let's see Poisson's ratio. So when you stretch a wire, what happens to the area of cross section? It decreases, right? So Poisson's ratio is the ratio of lateral strain in the wire to the longitudinal strain. Okay, so what do you mean by this? The ratio of lateral strain. Lateral strain is change in diameter per unit original diameter, or change in radius, you can say, per unit original radius. Okay, so it is delta D divided by D divided by longitudinal strain. We know it is, oh, it is longitudinal. I wrote longitudinal. I'm sorry. Okay, so delta L divided by L, but it will be with negative sign. Why there would be a negative sign? Because when the length increases, diameter decreases, right? Length increases, diameter decreases. Okay, so this is Poisson's ratio. Okay, so this very short topic was left. All right, so let's see this question. There is no change in volume of the wire due to change in its length on stretching. Volume does not change. The Poisson's ratio of the material of wire is, okay, so volume is constant. So volume is constant. Volume can be written as what? Pi r square multiplied by L, right? It can be written as pi r square multiplied by L. And we can write now from units and dimensions, we can write delta V upon V is equal to what? 2 times delta R divided by R plus delta L divided by L. Okay, and delta V upon V is 0. This is given, there is no change in volume. So what we can say is, okay, 0 is equal to 2 times delta R upon R plus delta L upon L, or delta R upon R is equal to minus half of delta L divided by L, because if you take this on left hand side, it will be 2 times delta R upon R equals to delta L upon L, right? Okay, and therefore if you take that 2 on the other side, actually minus 2 on the other side, delta r upon r equals to minus half of delta L upon L. And what do you want? You want delta r upon r divided by delta L upon L. Okay, and you want it with negative sign also. So if you take that negative sign here, delta L upon L in denominator, you get half. So Poisson's ratio is equal to this thing. It is half. That is 0.5. Option A. Metal rod is fixed rigidly at two ends so as to prevent its thermal expansion. If L, alpha and Y respectively denote the length of the rod, coefficient of linear thermal expansion and Young's modulus of its material, then for an increase in temperature of rod by delta T, the longitudinal stress developed in the rod is longitudinal stress. Okay, so we already know this thermal stress, right? What is thermal stress? It is Y multiplied by thermal strain. That is Y multiplied by alpha delta T. Okay, so thermal stress, is it inversely proportional to alpha? No. Inversely proportional to Y? No. Directly proportional to delta T upon Y? So it's directly proportional to delta T, okay, but it's not inversely proportional to Y. So this is also gone. Independent of L? Yes, it is independent of L. So option D is the answer. Right, Sanjay. It's option D. Next question. Two rods of different materials with coefficients of linear thermal expansions alpha 1, alpha 2 and Young's moduli y1 and y2 respectively are fixed between two rigid walls. They are heated to have same increase in temperature, same increment in temperature. If the rods do not bend and alpha 1 is to alpha 2 is 2 by 3, then the thermal stresses developed in two rods will be equal when y1 is to y2 is equal to. Again, this is very simple question. Thermal stress in first one is equal to thermal stress in second one. So y times alpha delta T for first one is equal to y times alpha delta T for second one. Increment in temperature is same, so we can cancel it out. Okay, so we have alpha 1 is to alpha 2 equals to y2 is to y1, and this is given. This alpha 1 is to alpha 2 is 2 is to 3. That means y2 upon y1 is 2 is to 3. So y1 upon y2 equals to 3 is to 2. Okay, option C is the answer. Right. Okay, so that was the last question. All right. So here we have finished another chapter, small chapter, but some questions are, I mean, at least one question is asked, most probably, from this chapter.